Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we are going to talk on the module entitled Hamilton's Principle and Lagrange's Equation under the paper Classical Mechanics. First, remember that we have obtained the Lagrange's equation from the D'Alembert's principle. So in this module, we will rederive the Lagrange's equation from a more powerful principle, which is the Hamilton's principle. And after completing this module, you should be able to learn about the Hamilton's principle of least action and its use in the derivation of the Lagrange's equation of motion. Then we will illustrate the power of this formulation by solving a few simple examples. To start, remember that non-relativistic dynamics in an inertial frame are described by Newton's equation, which are simply given as the applied force is equal to the rate of change of momentum, that is F is equal to P dot. In actual physical situation, the dynamical system in general is constrained by a priori unknown forces. So if one deals only with the applied forces, then one can immediately apply the Newton's equation. But in many physical situations, there are some unknown constrained forces. For example, the particle may be constrained to move on a given surface. The motion may be restricted within certain boundaries and so on. The constrained forces may be quite complicated, in which case one may have to look for alternative formalism. And one of these alternative formalism is the is based on Hamilton's principle. But remember that whatever the alternative formalism is, it cannot go beyond the Newton's laws, but it may result in the simplification of the problem and may even have a wider application. But the underlying physics cannot go beyond the Newton's laws. Historically, a minimum principle based on the notion that nature always acts is a very attractive thing. The minimum principle or Hamilton principle is extremely aesthetically attractive proposition, and historically this was first used by Fermat, and that the notion that nature always acts in a way that during the development of a dynamical system, certain quantities are minimized. This has been an alternative formulation of mechanics, and historically it was first used by Fermat to obtain the laws of reflection and refraction. And what he said was that the light in traveling from one point to another in a medium takes the minimum time. So the path which the light follows is the path of minimum time. So we will consider the Hamilton's formulation of the minimum principle. What is Hamilton's principle? The principle states that of all the possible paths which are consistent with the constraint along which the dynamical system can evolve from one point to another, the actual path that the system follows is the one which minimizes the action. And of course, we will have to define the action. What it means that if a particle under certain forces travels from point this to point that, so it can take all possible paths to travel from this point to this, but it takes only one path. How does one find that path? So according to Hamilton's principle, the path is one which minimizes the action. the action being defined as the integral of the Lagrangian over time between the endpoints, so that if a particle is starting from this point at time t1, which is this point at time t2, then the problem is what path does it take? In principle, it can take any number of possible paths, but the Hamilton's principle says the actual path taken by this particle is the one that minimizes the action. In fact, you will learn in quantum mechanics that what we are saying is true only for classical mechanics. A quantum particle in going from one place to another, in fact, takes all the possible paths, and the probability, its amplitude is the sum of all the probable paths with their respective probabilities. But in classical mechanics, the particle travels such that the action is minimized. So, we now will derive Lagrange's equation of motion from this principle. Let us consider a multi-particle system characterized by the Lagrangian function, which is a function of the generalized coordinates q1, q2, etc., and generalized velocities q1 dot, q2 dot, and maybe also a function of time t explicitly. This will represent as L a function of the set qk and a set qk dot and t, where the set qk and set qk dot are the sets of generalized coordinates and velocity. The action for this Lagrangian is given as the integral over dt from time t naught to a final time t. So, S is equal to integral L dt. Hamilton's principle states that of the various paths given by the generalized coordinates q1, q2, qn as functions of time and the generalized velocities q1 dot, q2 dot, qn dot, etc. as functions of time, the actual path followed by the system is the one for which the corresponding action is minimum. So, let us now from the definition of the action find out the condition under which this action is minimum. So, consider a two-dimensional plot in the time and the kth generalized coordinate plane. The dynamical system evolves from A to B, let's say along the path C, on which the generalized coordinates are given by the set qkt. Now consider a nearby path C prime, which is characterized by the generalized coordinate set qk plus delta qk, where delta qk is a small variation from the path qk. Then the change in the action delta s is given by the integral from t naught to t of the variation in the Lagrangian, which is a function of the set of generalized coordinates and generalized velocity integrated over dt from the initial to the final time t0 to t. Now this variation in the Lagrangian is given as a sum over j of the partial derivative of L with respect to qj dot, delta qj dot, plus partial derivative of L with respect to qj and delta qj integrated over dt. Now if you look at the first term in the integral, it can be integrated by parts because delta L by delta qj dot multiplied by delta of qj by dt into dt. This is how we have written this term. This integral is dl by dqj dot into ddt of delta qj dt. Integrating by parts, so we have dl by dqj of delta qj evaluated on the path where delta qj vanishes in the limit, and minus the ddt of dl by dqj dot delta qj dt. The first term vanishes at the end points, and therefore the variation in S is simply delta L by delta qj dl by dqj minus d dt of dl dqj dot multiplied by delta qj dt. Since delta s vanishes for arbitrary variations in the path, the Lagrangian, then we obtain the Lagrange's equation of motion, which is given by the integrand being equal to 0. That is, d dt of dl dqj dot minus dl by dqj is equal to 0 for all j's from 1 to n. These are the Lagrangian equation of motion obtained from the Hamilton's principle. The Lagrangian as defined is, however, not unique. We can add to it a term which is a total time derivative of any function j of t without in any way changing the equations of motion. We can, for example, write the action s as integral over L plus integral of a time derivative any function of any function j. That is, s can be written as the integral over dt of L plus dj by dt, which is equal to the integral from t naught to t of the Lagrangian plus the function j of t evaluated between t naught to t, and the last term being constant has no effect on the variation in delta s, and therefore, since the Lagrangian equations are obtained from the variation of delta s, the Lagrangian equations remain unchanged. Now I just mentioned very briefly the Lagrangian equation with undetermined multipliers. We have in fact obtained Lagrangian equations, but in the derivation which we had assumed that the constraints are holonomic and they can be expressed in terms of algebraic equations. If some of the constraints are expressed in terms of velocities, or if some of the constraints are in the form of non-integrable equations, like for example aixi dot plus bixi plus ci is equal to 0, etc., for arbitrary values of a's, b's and c's, then it is still possible to incorporate these constraints in the Lagrangian equation by means of the technique of Lagrangian undetermined multipliers. Take for example a non-holonomic constraint of the type that a function, a non-holonomic, a function of qi dot at t is equal to 0. So this is the form of a non-holonomic constraint which we have taken. This can be expressible as the sum over j of the partial derivatives of this function, which is a function of velocities as well as of coordinates and explicit time t, that the sum of partial derivatives of this function with respect to the generalized coordinates q j is equal to 0, where j is equal to 1 to m, and there are s such non-holonomic constraints corresponding to the value L, which goes from 1 to s. Then see the function non-holonomic constraint function we have represented as f with a subscript L. So where L goes from 1 to s. So there are s such non-holonomic functions, where s is the number of constraints and qj's are the generalized coordinates on which these constraints depend. Then the Lagrangian equations can be written as dl by dqj minus d dt of dl by dqj dot, which is equal to 0 in the case of holonomic constraint. Now if we have non-holonomic constraint, then they can be incorporated by adding a term sigma over I lambda I df cl by dqj is equal to 0, where qj's are the lambda j's are the undetermined multipliers. We will illustrate this with the help of simple examples. Let us consider a disk which is rolling down an inclined plane. So the problem is, we are considering is of a disk of mass m and radius r. It is rolling down an inclined plane without slipping. We have to write down the Lagrangian system and obtain the equations of motion. The kinetic energy of the disk is the sum of the translational and rotational energy. So kinetic energy is given by half my dot square plus half I theta dot square, where m is the mass of the disk and I is the moment of inertia of the disk about the central axis about which it is rotating. Now the system or this rotating disk is under the gravitational force, which is given by the potential energy U. The potential energy U is equal to mg L minus y into sine alpha, where L is the length of the inclined plane and L minus y sine alpha is the vertical distance as shown in the diagram. The potential energy is taken to be 0 at the bottom of the plane. The Lagrangian then is defined as the difference between the kinetic and the potential energy. So L can be written as half my dot square plus half I theta dot square minus mg L minus y sine of alpha. When the disk rotates by an angle theta, it traverses a distance r times theta along the plane. Thus, y and theta are related. So y is equal to r theta. Then we can eliminate theta from the equation and the Lagrangian simply can be written in terms of one variable y. So L becomes half m plus half I by r square y dot square plus mg L minus y sine alpha. From this we can immediately calculate the Lagrangian equations of motion by evaluating d dt dl dy dot minus dl by dy dot is equal to 0. So the equation of motion then become d dt of m plus I by r square y dot minus mg sine alpha is equal to 0, which gives us y double dot is equal to g divided by m plus I by r square sine of alpha. Now, one can immediately see from here that the acceleration is constant because g is constant, inclination is constant, mass is constant, moment of inertia is constant. So acceleration with which the disk rolls down the plane without slipping is constant. And another thing which you should note is that if instead of the disk we had a cylinder or a sphere or a ring or a spherical shell, the acceleration can be obtained by simply putting the corresponding expression for the moment of inertia. Let me consider the problem of a double pendulum now, which is a very interesting problem. Now, a double pendulum consists of two masses. So, two masses M1 and M2, each attached to strings of length L1 and L2 respectively. So, the first pendulum of mass M1 with the string length L1 has this free end of the string fixed at some point and is free to oscillate. The second pendulum is attached to the M1 and its length is L2. So, if we set up the coordinate system as is shown in the slide with the coordinate with the horizontal axis and the vertical axis such that the vertical axis is the x-axis and the horizontal is the y, then the Cartesian coordinates of these two particles M1 and M2, which are x1, y1 and x2, y2 respectively, then they can be represented in terms of generalized coordinates, which we take the angle theta 1, which the first pendulum makes with the vertical, and the angle theta 2, which the second pendulum makes with the vertical. So, in terms of these two generalized coordinates, theta 1 and theta 2, we can express the Cartesian coordinate x1, x2, etc. as x1 is equal to L1 cos theta 1, y1 is equal to L1 sin theta 1, and x2 is equal to uh, L1 cos theta 1 plus L2 cos theta 2, and y2 is equal to L1 sin theta 1 plus L2 sin theta 2. Then by differentiating them, we have x1 dot is equal to minus L1 sin theta 1 dot, y1 dot is equal to L1 cosine theta 1 dot, and likewise x2 dot is equal to minus L1 sin theta 1 dot minus L2 sin theta 2 dot, and y2 dot is L1 cos theta 1 dot plus L2 cosine theta 2 dot. Now it is trivial to write down the kinetic energy of the double pendulum. Kinetic energy T then is the sum of the kinetic energy of the first mass m1 and first mass m2, which is half m x1 dot square plus y1 dot square plus half m2 x2 dot square plus y2 dot square, and we can substitute for x dots and y dots from the relations above. The kinetic energy of the double pendulum is half m1 x1 dot square plus y1 dot square plus half m2 x2 dot square plus y2 dot square. x1, x2, y1 and y2 we have already expressed in terms of the angle variables theta 1 and theta 2, which are taken to be the generalized coordinates. So in terms of the generalized coordinate theta 1 and theta 2, the expression for kinetic energy takes the form T is equal to half m1 L1 square theta 1 dot square plus half m2 multiplied by L1 square theta 1 dot square plus L2 square theta 2 dot square plus twice L1 L2 into cosine of theta 1 minus theta 2 into theta 1 dot multiplied by theta 2 dot. The potential energy is given by U is equal to m1 L1 cosine theta 1 minus m2g plus L1 cosine theta 1 plus L2 cosine theta 2, which is equal to minus m1 plus m2 g times L1 cosine theta 1 minus m2 gl2 cosine theta 2. And the Lagrangian is simply given by the difference between kinetic and potential energies. Now, from these expressions, we can obtain the equations of motion, and it's not always easy to solve this. I will illustrate the solution by considering the oscillation to be very small. So when theta 1 and theta 2 are much smaller than 1, then sine theta 1 can be taken equal to theta 1 and sine theta 2 as equal to theta 2 and cosine theta 1 and cosine theta 2 as equal to 1. And after further simplification by putting the two masses to be equal, m1 is equal to m2, and the two lengths of the double pendulum to be equal to L1 is equal to L2 is equal to L, we get very simple equations, which are of course coupled equations, a set of coupled equations. We get the equation 2 theta 1 double dot plus theta 2 double dot plus 2g by L theta 1 is equal to 0. And the second set of equations theta 2 double dot plus theta 1 double dot plus g by L theta 2 is equal to 0. So the set of equations in theta 1 and theta 2 for small oscillations, for the simple case of m1 is equal to m2 and the lengths also being equal, is given by these two coupled equations. This coupled set of differential equations can be solved by assuming the solution to be of the form theta 1 is equal to a1 cosine omega t and theta 2 is equal to a2 cosine omega t, where a1 and a2 are constant. Substituting for theta 1 and theta 2 in the equations, omega and a should satisfy 2g by L minus 2 omega square into a1 minus omega 2 square a2 is equal to 0, and minus omega square a1 minus g by L minus omega square a2 is equal to 0. So that these are two linear algebraic equations in a1 and a2, and you know that for the trivial solution, for the non-trivial solution for these equations to exist, the determinant of the coefficients of A1 and A2 must be equal to 0. Therefore, the determinant 2g by L minus 2 omega square minus omega square, and in the second row, first column minus omega square, and the second row, second column 2g by L minus 2 omega square, the determined by formed by these must be equal to 0, which gives us the solution that omega to the power 4 is g by L whole square into 2 plus minus root 2. Thus, we have two eigenfrequencies, and the solution is given by these two values. As a final example, we consider the motion of a particle on a cycloid. Let a particle of mass m be moving on a cycloid, which is a curve whose parametric equation is given by x is equal to 8 times 2 theta plus sine 2 theta, and y is equal to a times 1 minus cosine 2 theta. The particle is moving under the action of gravity, and we have to set up the Lagrangian equation of motion and try to solve the equations of motion, at least for small oscillations. Now, for the infinitesimal distance element on the surface of a cycloid is given by ds equal to under root dx square plus dy square. There's always the line element or distance on the surface of any, between 2 points on any surface, where the points are separated by small variation of in the x and y coordinates. So this infinitesimal distance ds is then can be written in terms of the generalized coordinate theta by using the parametric equation of the cycloid. So substituting for x, using the expression for x and y to calculate dx and dy, the line element of the infinitesimal distance ds is written as a into 2 d theta plus 2 cosine 2 theta d theta whole square plus 2 d theta plus 2 sine 2 theta d theta whole square under root, which is equal to 4a sine theta. So the element of length on the surface of the cycloid in this is given by 4a sine theta. The kinetic energy being half m, the velocity square, which is ds by dt whole square, is then 8m square cos square theta, theta dot square. The potential energy is given by mgy. Substituting for y is mga 1 minus cosine 2 theta, and therefore the Lagrangian is given by t minus u is equal to 8ma square cosine square theta, theta dot square minus mga multiplied by 1 minus cosine 2 theta. The Lagrangian equation of motion, namely d dt of dl by d theta dot minus dl by d theta is equal to 0, can be easily computed, and the equation of motion we get is 4a cos square theta, theta double dot plus g by L sine 2 theta is equal to 0. So just note one thing, that we have only one generalized coordinate theta. Now for the small oscillations, cos theta is 1 and sine theta is theta. So this equation then in that limit reduces to a very simple equation, 2a theta double dot is equal to minus 2 g times theta, which is the equation of a harmonic oscillator with a frequency omega is under root g by 2a. So students, let us summarize what we have learned in this module. We learned that the principle of least action is a very powerful method which can be used for an alternative formulation of mechanics. In fact, the method has been used for the alternative formulation of classical mechanics as well as the quantum mechanics. And the principle, which is enunciated by Hamilton, it states that a dynamical system evolves along a path that minimizes the action. The action being defined as the integral of L dt. Thank you.